One start recording. Let's get rocking and get rolling. So, did you get a chance to watch the rest of those videos?
I watched 3 and 5, right?
It's supposed to be 3 and 8, but
Really?
yep.
Ha! Well, now I know more about the exponential derivatives than I probably needed to,
Well,
and how they refer to themselves. But actually, it helped me because it kind of, I mean, I still have a very weak grasp on it, but he kind of explained the constants, the natural logs or whatever, that kind of like
oh, yes.
seemed a little bit like how you were plugging arbitrarily a constant into our exponential functions. So, sort of, kind of, but yeah, no, I
Well,
totally messed that up.
I mean, that's fine. Like, that's still good information. We're not going to use it, but it's good to know. So, like, yeah, I was just watched 138, 1238, just for time's sake. But if you manage to have time, watch the whole thing by all means, because it's all good stuff.
Right, well, I did watch 3.
It
was mostly review from your session.
Oh, well,
However,
that's all right. So, for those people playing at home, we're talking about the 3 blue 1 brown calculus videos. So,
also known as the 3 brown 1 blue calculus videos, because I can never get that right.
Well, I'm sure the Google search is like able to figure that one out. If you put that in. So what we had, basically we were like, all right, we have some graphs, and one of them we'll just have like 3 of them, and one of them might be like this constant value. So it's and if this is, let's say, f dash of x, equals some constant like 1. Then we could integrate it up and we end up with a graph that looks like that, and that's like f of x equals x. And then if we integrate this again, we end up with a graph that looks like this. F of x equals half x squared. So this is sort of basically what we were doing yesterday. So we can integrate up this way, and we can differentiate to go back down this way. So, are you reasonably happy with everything we have here?
Yep.
Cool.
I mean, I still don't understand it, but I'm sure when we do it, it'll make some sense.
So, there was one last thing. For some reason, I blanked on this last time, and I was like trying to remember how we did this. So, basically, the integration thing, and this is probably what you'll have missed in the videos, because I think they do this in 8. So when you differentiate, we went over this in quite a bit of detail. It's like, all right, what's the slope at this point? There, it's like, it's 1. And if we do this over here, it's like, what's the slope at this point? We look at it over here. It's whatever that is. So that's differentiation, tells us the slope, but integration tells us like the area under the graph. And you can sort of see how this works. It's like, all right, let's say if this is 1 and this is 1, we have this block here. And then if we look over here to like the position 1, we'll look up on this graph and it's like, oh, look, the area is 1. So it's, 1 times 1 over here for the area. And then we could move along and we'd be like, all right, what if we want the area at 2? And we're looking at the area under this graph, and we're kind of skipping over a bit here, as in like where do you start and where do you end? We're just going to sort of start at 0 and hand wave that away. But we've got 1 times 2, and we look over here and it's like, oh, here's 2. We look up this graph and it's like, oh, it's 2, and so on. So, and then we can do this over here. So if we I'll do this in orange, maybe. We'll try green. If we're looking at the area under this graph, and I know I just haven't drawn it quite perfectly, but let's say we want, the area up until, say, 3. And so what we're looking at is, geometrically, we've got a triangle, and, that's this triangle here. And it's, it goes from 0 to 3, so this is 3 long, and we know that this has a slope of 1, so it's like for every 3 units that we come across, we also go 3 units up, so we know that that's going to be 3 here. So, if we were doing the area from here, it's like, oh look, it's 1 times 3. We've got the area here, but we also know, so this is going to be 3. And then when we do this, we can calculate this geometrically. We know that the area of a triangle is basically the area of the rectangle that encompasses it, divided by 2, because we've chopped off this half, so it's like 3 times 3 divided by 2, which is obviously 9 divided by 2, which is 4.5. But you can sort of see that we can do this like at any point, so we could just pick some random point there. It's like, okay, that point is going to be, let's call it S for fun. Actually, let's call it X. Oh dear, what happened there? Okay, let's call this point X, and it's going to, and this is different to the X we're using here. Function. Yep. Mm-hmm. So, and we just basically do the same process. It's like, all right, if this is our triangle, we have X times X times X divided by 2. Oh look, this is half X squared. So this is how we sort of geometrically get this integration thing going. So it's like, okay, that's how we got that one. So happy with that so far?
Yeah. I'm a little slow on the uptake when it comes to factoring, because it took me a second to see that you took, that's X squared and then it's divided by 2. But instead of describing it that way, you turned it into a product to multiply it by X squared.
Yeah,
which is fine. That's the stuff that from like high school math I have to brush up on. But yeah, I get it.
Yeah, that transform there is fairly straightforward. But yeah, it is a transform of sorts. So the process that we use in general to do this, because you can imagine it's like, oh, what if I have this function and I want to integrate it again? Then
so why would we? I mean this kind of begs the question, like, why are we constantly integrating this and what are we getting from it? Like in the first case, like I guess when we've integrated the one time to f of x is equal to x, I can kind of see how that's useful for getting the slope. And then we can we use the next one to get the area, I guess. That you've defined in the bottom one, but I don't know. Why do we do this?
Okay, so let me just finish off that last thought in a slightly more detail. So it's like, here's x, here's x, and what you'll find is that this value here, when you chart it up here, is going to be half x squared. So the idea is, okay, we have this area under the graph, and then we're going to integrate up and get this graph here. And what we can do is we can look at a position on this graph and get an area for the area under this graph between, roughly speaking, between the 0 and this thing.
Right. Even if the graph is this sort of parabolic shape, you can still do it, because
exactly.
That's what the half of x squared is like accounting for that.
So you'll find, so I mean this one's trivial because you can just do this geometric process, but you can imagine it's like, all right, now I want to find the area under this one. It's like, all right, well, that graph is going to look like, and now I have to do this on the fly. I think it's 1/6 x to the cubed. Yeah, I think that's that. And hang on, this is where we're going to bring up Google and get Google to do this for us.
You're doing this so that you can get the area under the curved line, because the only thing you're getting right now is the slope or the rise over run of the curved line.
Hang on, let me just X. Okay, here we go. Okay, so I've got that graph now. Now I can see what it is. So what I'm doing is, when I integrate it, I'm getting this area here, and so what this graph is going to look like is this, and I'll bring it up on screen.
I guess I'm trying to ask, is this sort of like a successive thing where you're trying to get the slope, and then you integrate again to get the area, and then it's like slope and then area?
No, sort of. Like you're on the right track, but okay. So what you're doing when you're integrating this way is you're getting area, and when you differentiate this way, you're getting slope.
Right, but I guess I'm questioning is that your fourth one, you said that you're going to try to get the area under the third one.
Yes, so you can repeat this process.
Was the third one? The third one was trying to get the area under the second one?
Exactly. And then the second one gets the area under the first one.
Okay.
Whereas, but you can go the other way. It's like, all right, the third one is the slope of the fourth one, and the second one is the slope of the third one, and the first one is the slope of the second one.
Right. Okay.
So I believe this is what they describe as is that the fundamental theorem of calculus? I can't remember what it is.
Is it the chain rule? Oh, no, that's something else. No, there's the chain rule, the power rule.
So the chain rule and the power rule are techniques that you use. So you'll notice we did a maths operation to get that, and then I just sort of did this one in my head to get, this is how you integrate.
That's the power rule, right? Yeah, that's the power rule.
I believe that's the power rule.
I kind of saw that in the video where he's
maybe. I can't even remember the names. Like I was saying, if we have this problem, it's like we go to the fine folks over at wait for it to load over at Wolfram Alpha, and we're like, all right, integrate 0.5x to the power of 2 dx. So this dx is like with respect to x. We're going to integrate this. It's like, oh, look, we've got 1/6 x cubed. And here's the same graph. So that's how you'd start to deal with it. So you can imagine, like, if I was like x, oh, let's do something ridiculous, like x to the x dx. So here's our input. So integrate x to the x with respect to x, and you get, like, holy cow, you get this kind of nonsense. I thought the result of this was supposed to be a fair bit more simple than that. But
that looks like Google hunting chalkboard stuff.
Yeah, this is painful to look at. I thought this was actually, maybe it's not even integrable. That's fun, but yeah, that was a fun one. But you can be like sine x, let's say sine 3x dx. So we can do like trigonometric functions, and we can integrate them, for example. And it's going to show us what this is. It's like, oh, look, here's the result of that. And so if you get something complex and you're not a mathematician and you just need an answer, you just go to Wolfram and it's like, oh, we're done. And here's this constant that we were talking about. Remember when we can like shift the integrated graph up and down?
Right.
So that's there as well. So let's try this. So the process for this one here, this process here, is, say we have, let's In fact, actually, let's start by doing this process here. So we're going to differentiate. So if we have a function like f of x equals 7x3 plus 5x squared plus 3x plus 4, and we want to differentiate that. So we're going to get f dash of x. So the process for this is we take this coefficient here, this exponent, and we multiply the coefficient by that. So we're going to get 21
X to the x squared.
Squared. So we then subtract 1 from the exponent. So and then
yeah, he was explaining that in the video.
Okay.
But...
Oh, that's good. So you should be nice and familiar with this. So we get 3, and then this just drops off the end, because you can imagine that's x to the 0. So it's like 4 times 0 is going to be 0. So it's like all of this is multiplied 0, so it all goes away.
Right.
So we get that, and then let's say we want to go and integrate it again. So we've differentiated it. Now let's integrate that. So we're going to get f back, vaguely, and so we reverse the process. So we're like, all right, we're going to add 1 to the exponent. So we're going to get x to the 3. And then we're going to divide this, and so look, we get 5x squared plus 3, and this is x to the 0, so we're going to add 1 to the exponent and then divide 3 by that, so we're going to get x3 plus some constant. And this is the constant we had before. We were like, well, we've got a graph, and it could be there or it could be there, and here's our...
Right, doesn't matter, it's up to you.
See. Yep. So it sounds like this is something you're pretty familiar with.
Well, familiar isn't the right word, but I can do that.
Good.
Officially as of today.
Excellent. Well, I mean that's a good start. So yeah, no, I'm happy with that. So we're comfortable with roughly what these things mean. So let's start applying this to some physics. So you can imagine that if this, if I wanted to just slap some labels on this thing, I'm going to ignore this one for now, although I won't scribble it out. If this is like acceleration, and we integrate acceleration, we're going to get velocity. And we integrate velocity, we're going to get position. And by the same token, if we differentiate position, we're going to get velocity, and if we differentiate velocity, we're going to get acceleration. Is that something you're reasonably comfortable with?
I mean, you kind of blew my mind there, but it makes sense. Yeah, that's really cool. That just happens to be true, or that's just like how the world works, therefore...
I mean, that's how these things are defined, is...
Right.
And you can imagine, so if we apply some units to these...
I can see acceleration on its own. It's a scalar value, and then you've basically turned it into a vector of acceleration over time, or distance, sorry, over time. And then the interesting one is going from velocity to position, but I guess that's just integrating the result of the time that you've been at that velocity that puts you in a particular place.
Exactly. It sounds cool. So and you can, and hopefully you can see it's like the reason that the area here becomes how far you've gone. It's like, well, I went that's a good velocity. Yes. No. So I went
that many
this fast for that long, and I went like this fast for that long, and this fast for that long, and this fast for that long, and that's roughly the area. And so that's how far I've gone.
Right, that's how much area you've displaced over that period.
Exactly. And so what I wanted to draw here is like, okay, if we measure position in meters, we're going to measure that in meters per second. And this is going to be meters per second per second. And hopefully that also makes sense, why that's the case.
Well, meters per second,
So
meters per second squared is interesting.
So the way this works is it's kind of like the same thing we're doing here. We've got meters per second, and this is just a way we can notate it, because it's kind of algebraic. It's like we divide by seconds, and we divide by seconds again is mathematically equivalent to dividing by seconds squared.
Right. That's just my factoring weakness at work again. That's cool. I'm not used to thinking of acceleration as meters per second. Like what is, like, when you put your foot on the gas, like we already talked about, or the video talked about how the odometer isn't and nothing really is an instantaneous rate of change. Always comparing some small amount, which is obviously even with the delta, like what the d is in the calculus.
Yeah.
Some arbitrary thing approaching zero. How does that gel with this concept of acceleration? Like, what is acceleration then? It's
okay.
Like I only think of it as I only have been thinking of acceleration as just without the time component of velocity. Just like, this is how much oomph I'm trying to apply, like how much sort of force I'm trying to push through whichever machine I'm in. So it's hard. Yeah, it's really hard to think about that for me to think about that in a sensible way, especially with per second.
Well,
I get it now. Yeah, Well, how much meters per second is actually getting out the door per second? Like, that's exactly what it is. Yeah, that's really.
So we've got a second.
Yeah.
And we're adding it.
Yeah.
We've got another second. We're adding another thing.
That much. Yeah. Which will dictate your velocity, because this is how much you're, increasing. This is the unit that you're increasing your velocity by on a second-to-second basis. Like,
exactly, and then it's exactly the same here. So every second we're adding another meter here.
That's right.
Exactly. So that's good. That's good, because it means you're starting to get the concept. In fact, it sounds like you actually got the concept, which is the important bit. So so now we can move on to a little bit of implementation. So in a game scenario, there's kind of two ways we can handle this. What we can do, let's write these down. We can either go, and I think there might be better terminology for this, but I'm just going to use these because they're close enough. So we can go parametric, or we can go iterative. So we can go parametric or iterative. And you can imagine parametric is basically what we've been doing here. So if I'm like, all right, I've got this, I'm accelerating with the constant acceleration of 1, and we're starting from 0 everywhere. It's like, all right, if I have a function that tells me my position, that function is just going to be like, half x squared. And I can just plug in whatever I like here. In fact, let's introduce the concept of time, because that's obviously, we're in a game, we're animating these things, so it's like we want the time. And this gives us this lovely graph that we're all familiar with now. Iterative would be the case where it's like, I'm basically doing the same thing, but now I'm storing some state. So it's like, all right, if I just draw this out, for example, it's like, all right, well, we were accelerating, and we did a frame, and we accelerated there. We got some position, and we've got a velocity graph that's also increasing over here, perhaps, and maybe we're tracking the velocity as well. and then I, applied some more position. Sorry, I applied some more acceleration, and then a bit more, and then suddenly I started decelerating. So I'm like applying some negative acceleration. So and every time step, I'm saving out what the thing is, and this lets me do things like, for example, changing what the inputs are at this point, based on like user input or a collision or something.
Right.
But the important thing is,
why wouldn't you be able to just plug in the parametric at every update tick, and then you'd still get the same?
Well,
oh yeah, no, never mind.
Yeah. So what?
Because it would be instantaneous change. You basically just like press a button, you'd be that fast, like as opposed to like ramping up or
exactly. And the thing is, like in between each time step, so between here and here, we still actually want to do like this sort of process, like this little time step. If we've done the maths right, this is just like a little slice of this.
Right.
And that will become important if we're trying to do something really accurate. You can imagine that there are simulations that, if we're lazy about this sort of thing, and we don't consider the fact that we're doing integration and differentiation on these things, you can imagine, we might just be like, oh, well, we add some position and we just add it, and then maybe we add some position, then we just add it, and then we're adding a bit more position here, and you'll start to get these, tiny errors in our physics. So considering the fact that we've got integration happening is important for accuracy.
Right. This is almost exactly the same as when I kept trying to not care about the basis vectors and would just like add stuff to the end. I'd always get errors because I was adding these scalar values, and this would be exactly the same thing because we're not considering the tiny changes, right? The tangent line that's getting closer to 0. We're not looking at that. We're always gonna miss the target, right? Because we're never gonna be in the right space, I guess.
Sort of. Like,
yeah, I'm good with sort of.
Yeah.
I'm trying to relate it to it, trying to relate it back to the sort of practice of Cartesian whack-a-mole, just adding numbers and hoping it works out.
Yeah.
You can't, is all I'm trying to say.
Yeah. So I mean, like, certainly in this sort of thing for like some games, and I'm sure some of my early works were similar to this. This area here is is actually relatively small, because this half t squared is probably going to be a fairly small value compared to like the velocity. So I'm just trying to work out in my head what the actual practical thing is. So if we're doing the iterative method, we're storing state. So you can imagine we have like some struct foo, and it's got like a float velocity and float position. You can imagine like, all right, I want to apply a constant acceleration. So every tick, I'm going to be like, all right, well, velocity plus equals, let's just say the acceleration is a, and then position plus equals velocity, and maybe I multiply these by t if I'm like how long does it tick, like t equals frame delta. So you can imagine I've done this, and this is going to be fairly accurate, but what you'll notice here is that I'm adding these segments onto P, and it's kind of like, I know this is like, if I zoom in on this little segment here, let's try and match the colors. what I've gone and done is I've added something onto P. So it's like, all right, I've just gone add, and this is going to do this. Whereas what I really wanted to do is I wanted to actually consider the fact that this is an integration, and so what I would do is I'd then end up here. So this has got some curve on it because, you know, the actual underlying math says that that's a curve, and so I've missed something plus something here, which is something that we can get into soon. So, but does that make sense?
Totally.
Excellent. So this is why we're approaching it from the parametric perspective first, is because that's sort of like that's actually the simpler one. Like this is simple, but it's wrong. I guess is what you'd say.
It's more difficult to get it right.
Yes. But eventually we will want to do this because, you know, we want, you know, collisions and user input and stuff. Okay, so let's see. So we want a concept of time, as you know, as you can see. No matter what we're doing, like everything is about time. So usually with time you want to measure it in seconds. In some specialist circumstances, maybe you want frames. I know for River City we did frames because we were, I guess we were working in integers largely, and I guess this was easier for that particular thing. But if you're working in like floating point largely, generally seconds is fine because you just like how to describe it? It's like, you know, every tick is 0.00166 seconds.
Right. Well, hold on a second though. You said that. I mean, I didn't realize that. I mean, that's interesting. I thought we were using time. Like I know we have so in River City we had the frame counter, which was literally just ticking a frame. But or incrementing a frame by one. But when you say, what do you mean by frames in this case? Like, do you mean literally every tick is 1, 2, 3, 4? And we use that to determine the physics, or do you mean like ticks?
So let me, I guess, I blasted through that a wee bit quickly. So let's say we have this here, or even this here. This is a lot of arrows pointing to it now. Let's say we have formulas that look like this, and we're working this through. You can imagine if we're using seconds, we're like, all right, well, what's the velocity? Velocity equals plus equals acceleration times 0.001666. I think I've got the right number of zeros in there. Whereas if you're working in frames, you might end up with a thing that's like 0 plus equals acceleration times 1, because we've stuck in one frame. Now what happens is you then have to be really super consistent about, you know, are we measuring everything in seconds, or are we measuring everything in frames? So this acceleration value here needs to be in meters per second, whereas this acceleration value here needs to be in meters per frame. And the actual value of A will be different between these two systems to get the same result.
Okay, interesting.
So in fact, and you know, if we're working in River City, we've actually got meters. We've got pixels per frame, and so these are equivalent. Like it's the same formula. It's the same acceleration times time.
Can you ever say that one is better than the other, or is it really game dependent? Like if you were going to do like a line art, like Geometry Wars, you would never want to do it one way versus the other.
So we got some we got some advantage from the fact that because we were working in integers, the fact that this is 1 is a massive bonus to us, because we can just skip past doing like, you know, if we have like where is it? Oh, I guess here it is. It's like half t squared. It's like, well, that's like t times t. That's like 1 times 1. So we can already just completely get rid of that factor. It's like half. And then I think we got rid of the half somehow as well. So this is like just algebraic manipulation to try and reduce the amount of maths. And also because we were working in pixels, you know, integer pixels, it's like the last thing we want to have appearing is this like fractional value here, because it's like we don't want to track that. Whereas if you're working in floating point, it's like, oh, this is trivial to deal with.
Right, and in fact, that's kind of why we had to switch physics engines, right? Because we were tracking the floating point on, like, we're building geometries. I think this predated you, but we're building geometries underneath the character.
Yeah.
The character was actually triangles, but then when you try to present that, it had a whole bunch of problems. So,
yeah, exactly. So
it's worth knowing that that's very, you know, you can change the math to get an advantage.
That's like we did that. Like, it wasn't just for this, but it was basically this writ large. It was this across multiple systems. It's like, you know, we can get rid of a whole lot of fractional values just by building a system that's like specifically designed to do this sort of thing everywhere.
Makes sense.
Yeah. So let's bring up some code. So as I was saying, we need a concept of time. So let's roll down to update over here and just like float time. And we're just gonna, what have I got on space? Oh, space does separation. I'm gonna move space over to S for a sec.
Where did you go?
Sorry.
Where did you just float
I
something?
Ahead. I wrote float time equals 0.
Got it. Okay.
And then I rolled down here. I was like, I want to use the spacebar for something else. So I'm just going to change that to S for now for separate. And there's method in this madness. So I'm going to be like, if input dot key is key down, keys space time plus equals. What is the thing? It's game time. Dot elapsed game time dot seconds. So
total seconds?
Yeah, I knew it was wrong the second I wrote that. Total seconds, and I'll just cast it to float for now. Oh yeah, I wanted to and if you're not holding down space, else, because we want to reset, else time equals 0. So now we have a concept of time. What I wanted to quickly say is floating point accuracy is only really good enough for short timers. So if this wasn't getting reset, if this was constantly advancing, particularly if this was like, you know, just tracking the game time, floating point is not accurate enough to do that over a long span of time.
That's why total seconds itself is double?
Yes, exactly. So that's something that we can go into more detail on this specific implementation of like how floating points get stored and, you know, why that is. So that's something we should talk about, but we will talk about that on another time. But it's worth thinking about. But for the time being, float will be fine because we're resetting it.
Is that an X and A specific thing? Sorry, F and A, whatever.
No, that's sort of a game specific thing. So you can imagine, if you remember, we were tracking frames. So we had, where's calculator? So can I do this on the fly? Let's see. So we had a I think it was a 32-bit value for frames. So we had 2 to the power of 32. I think we were unsigned. Let's just say we were unsigned. So we could store values between 0 and this many. So this is heaps. But we start doing the division. It's like, all right, that's frames. So that's how many seconds we have. So then seconds would be minutes, and then minutes would be hours, and then divide that by 24. So we had 828 days divided by 65. So we could run the game, and I think we must have been assigned. So in fact, it's probably divided by 2, but still. So we could run, like someone could play River City Ransom for about a year and a bit. And at that point, the frame time would tick over, and stuff would start to go really, really badly wrong. So if anyone's like, it's been out for a little over a year now. So if anyone started playing, the moment it came out and just kept the game running, you're gonna.
Why didn't we make that an achievement?
Because then we'd have to track it, and I don't want to test that.
Oh yeah, testing that would be hard.
Yeah.
It's interesting. This actually reminds me also of just randomly, like F&A. Ethan posted on Twitter about some bug that came out where somebody said somebody finally ran this thing for like 3 years or 2 years or something and got this bug.
Yep.
From OpenAL or some kind of internal counter. So I guess it's like real life, right? It's just whatever is good enough, and nobody in their right mind would be actually playing this. Chances are, if it was running for a year, they're not actually attending to the game. So it's pretty hilarious.
Exactly, and it's something like that quick little calculation. That is something that I did because I'm like, all right, we can deal with a year. If it was like, oh, the game runs for like 2 days and then falls on its face, then I would have been like, maybe that's something we should do something about. But it's like a year, that's fine. Floating point does something slightly different. So you can imagine let's do it this way. You can imagine if, for example, floating point only had 1 digit precision. So it's like it can store 0.1, 0.2, 0.3, and so on. But when you're up here, it's like 1, 2, 3, and then if it's like 10, 20, 30. So floating point sort of works like this, and it can store more digits. But let's say for sake of example, it can only store 1 digit. So if we're adding time to it, so every time we're going, every frame is like plus 0.1, plus 0.1, we get 0.3, 0.4, and so on. Well, 0.9, 1.0, and then we're going to try and add 0.1 to it, and we should get 1.1, but we can't store 2 digits of precision, so we're suddenly storing 1.0, 1.0, 1.0, and suddenly time has stopped because we've stopped adding values onto this time. So that's sort of the different way that floating point fails, unlike integers, which just wrap around.
Right.
So we'll go into more detail on that another time.
But just to reiterate, in the case that we happen to be like in the hypothetical world where we were using floating point for River City, if we ran it for like the year or whatever the number turns out to be, basically time would stop as opposed to rolling over.
That is a rough way of describing it. Things would actually go wrong a bit earlier because I suspect because we're doing calculations with time, for example. So if we're for example, if like you can imagine, it's like, all right, like divide something like this by 2 or something. So it's like 0.9. We should have 0.45. That's going to be like 0.4.
It's kind of like its own game. It's like the players or the characters in the game start realizing they can't jump anymore, or like things sort of degraded multiverse type of problem.
Exactly. So that's the sort of thing that you do have to consider when you're dealing with large ranges of floating point values is that, you know, things will degrade. And so, for example, when you're writing a physics engine, it's one thing you have to think about is like, what kind of scale are you going to tune your physics engine for? Because, you know, if you have like an object that's like, you know, 4,000, for example, and we're, you know, pretending we only have one digit of precision, you know, you've got an object that's like 4,000 and that's going to collide with something that's like 0.4 in mass. You know, we've got this mass calculation down here, and we're like, you know, multiplied by the mass divided by the mass plus the mass. You can imagine that very quickly, if you try and throw this into that formula, something's going to go horribly wrong.
Just because of not being able to store that much precision?
Exactly.
Oh, you're talking about DP1, of course. Yeah, you're gonna go.
Yeah.
It's almost gonna go to 0, and you might even explode because of a divide by 0.
Yeah, exactly. So from memory, I think float is 6 to 7 digits, and it depends because, you know, these are decimal digits, whereas you know, these are stored in binary. Double, I think, is 11 to 12 digits from memory. But if you're actually working these things out, you actually, you know, if you're being really careful about it, you would think about the actual binary encoding of it. Okay. We're actually starting to run out of time here.
No, we just added it. So what do you want to do with it? Do we have time to do something with it, or are we we need to hold off for another day?
Well, I wanted to get into moving things around based on time, but I'm thinking we're starting to run short on that, on actually doing that. So let's just prove to ourselves that our little time thing is working, let's say.
Sure.
So let's do something just for funsies. Calculate separator. Where's draw? So did you end up drawing the axes into the thing?
I think so. Yes.
Cool. Just trying to work out.
Oh, wait. I don't.
These ones.
I mean, yeah, the pink arrows, right? Yeah.
Oh no, I meant the 0 axis. Is that it? I think that's it.
Yeah, I don't have that. I'll just have to tap that out.
Yeah, just slam them in there. So let's draw a little like a clock. So give you a sec to catch up.
Oh, I see what you're gonna do. Almost there. I'm just gonna unit Y.
Yep.
Here and here. Looks right-ish.
Pretty sure that's right.
Okay, good enough.
So let's just say line batch.arrow from vector2.0, and then we want to go and rotate this thing. So we already have the mechanisms to do rotation because we wrote them. So here's some really long distance remembering of stuff. What did we call it? I think we called it transform 2D. Dot create rotation by time. Dot. How do we do a transform?
Don't we need to mod that by how much? By 360.
The amazing thing about rotation is that you can go above that. So
it does that for you, basically. That's awesome.
Exactly.
Yeah.
So,
okay. I should have known that. Okay.
Yeah, no. So here's sine x, and so it keeps going.
Right, there it is. Yeah.
So we're going to rotate a unit vector on the x-axis, and then we want this. Basically, we just grab the rest of this line here.
Why the x-axis specifically?
Well, it doesn't really matter. We just need some distance out that we're going to rotate, and unit x is sort of a traditional.
Oh, I see.
Traditional
Right.
one.
Plus it's basically the same as unit y in this case anyway, so it doesn't really matter.
Yeah. So I've just copied pretty much the rest of that line.
I'm going to ham-fistedly.
That's all right. It's pretty straightforward. So this is the nice thing about once you start to build up this like set of things, like, oh, I just want a rotation, let's just slap that in rather than having to go back and be like, oh, sine, cos, da 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 da. So in theory, we have our time vector, and if we hold down the spacebar, hey,
it goes backwards.
Well, that's because we fixed up our space, our like Cartesian space, and so a positive rotation goes counterclockwise. So I mean, if we wanted to make it more like a clock, we could do that. So we just
no, it doesn't. It doesn't matter. But see, I don't even like. I'm all the way back to why did you change the unit vector to? I'm not going to. I'm just gonna change the negative on the time. Haha. I want to see this explode. Oh, where am I? Okay. Whoa. It doesn't explode.
Nice.
But why did you do that?
Oh, I just did that so it looks more like a clock.
Oh, mine's still going backwards. Oh no, it's not. Okay. I'm just sorry. What did you do differently than because you changed the unit vector?
I changed this to unit y, so it pointed upwards by 1 unit to start with. So at time equals 0, at 0 rotation, it's going to be pointing straight up and down.
Oh.
And then negative time just lets me rotate clockwise.
So the only difference here is that my arrow is pointing along the x-axis, and you're just going to start at the green arrow. Okay.
Yep. Exactly. So that was a good way to finish up the last 5 minutes. And now we've proven that our input code works. So now we're in a really good position because we have some time.
Sorry.
We have some time. So next time when we come back to this, we can actually do a bit of physics with this because now we have a working time value. All right. Any questions before we finish off?
No, I'm good.
Excellent.